Tonight, before the world grows silent and your thoughts begin to soften, there's something quietly astonishing to remember. You are floating inside a structure no human truly understands. Not your room, not your city, not even your planet, but space-time itself, the invisible stage that holds every star, every breath, every second of your life. Scientists can measure it. They can write equations about it. They can detect its ripples from black hole collisions. And yet, even after more than a century since Einstein reshaped our understanding of reality, the deepest question remains unanswered. What is space-time? Really? In the reference script, we learned that gravity is not a pull but geometry, that time runs differently on GPS satellites, that black holes bend reality so intensely that equations collapse into infinities. These are not science fiction ideas. They are measurable facts. But here is the part that should make you lean closer. The two most successful theories in physics, general relativity and quantum mechanics, refuse to cooperate when describing space-time at its smallest scales. The universe works. Our math works, but the deeper explanation is still missing. And that's where tonight begins. Welcome to Velorin, Sleepy Space Mysteries, where we gently wander through the quiet edges of understanding. If you enjoy drifting into the universe like this, subscribe, like, turn on the notification bell, and consider joining our membership to support this calm corner of curiosity. Before we continue, tell me in the comments where you're listening from tonight. I'd love to see how far this quiet signal travels across space-time. Let's begin again, slowly, with the quiet revolution that changed everything. Before the early 20th century, gravity was understood as a force, a pull, an invisible hand reaching across space, drawing objects together. This idea, shaped by Isaac Newton, worked beautifully for centuries. It predicted the motion of planets, the fall of apples, the rhythm of tides. It felt intuitive. Something pulls, something moves. Simple, direct, comforting. Then came Albert Einstein, and with him, a shift so subtle and so profound that even now it can feel difficult to internalize. He did not say gravity was stronger or weaker than we thought. He did not adjust the force. He removed it. In his description, gravity is not a pull at all. It is geometry. Mass and energy do not reach out and tug on distant objects. Instead, they shape the structure of space-time itself, and objects simply move along the curves that structure creates. Matter tells space-time how to bend. Space-time tells matter how to move. That is the entire exchange. First, this sounds abstract. Geometry guiding motion, curvature replacing force. But let's ease into it gently. Imagine, for a moment, a wide sheet of fabric stretched out before you. If you place a heavy ball in the center, the fabric dips. If you roll a smaller ball nearby, it curves inward, spiraling toward the heavier one. From above, it looks as though the smaller ball is being pulled. But in truth, it is simply following the slope beneath it. This is the classic fabric analogy. It has appeared in documentaries, classrooms, and quiet late-night science videos. And it helps, but only to a point, because the fabric in that demonstration is sitting in another space. Gravity is pulling it downward. The dip depends on something external. In the real universe, space-time does not sag into anything else. It does not hang inside a larger room. Curves within itself. There is no outside. So the analogy is a starting place, not a final answer. The true curvature of space-time is four-dimensional, woven from 3 dimensions of space and 1 of time. When mass sits somewhere, it does not just curve space. It also alters how time flows. That is where the idea becomes quietly astonishing. Because this is not metaphor. It is measurable. In 1919, during a total solar eclipse, astronomers measured the positions of stars appearing near the darkened sun. According to Einstein's equations, the sun's mass should curve spacetime enough to bend the path of starlight passing close to it. And during that eclipse, the stars appeared slightly shifted from where they would normally be. The light had curved, not because it was pulled by a force in the old sense, but because it followed the geometry shaped by the sun. Light, which has no mass, still follows curvature. That alone tells you something profound. Geometry governs everything. And then there is time. Einstein predicted that the stronger the gravitational field, the slower time would pass. Not in a poetic sense, in a literal one. A clock placed closer to a massive object would tick more slowly than one placed farther away. For decades, this sounded like a strange theoretical consequence. But atomic clocks are patient. They measure with extraordinary precision. When scientists placed identical atomic clocks at different altitudes, one higher, one lower, they found exactly what relativity predicted. The lower clock, deeper in Earth's gravitational field, ticked more slowly. The difference was tiny, but it was real. And here is where the abstract meets your daily life in the quietest possible way. The satellites that power GPS navigation orbit Earth thousands of kilometers above you. Up there, gravity is slightly weaker. They are also moving very quickly. Both of these factors affect time. According to relativity, their onboard clocks tick at a different rate than clocks on Earth's surface. If engineers ignored this, your GPS location would drift by kilometers within hours. The map on your phone would quietly lose its grip on reality. So every single day, without fanfare, relativistic corrections are applied. The curvature of spacetime is accounted for. Time dilation is adjusted. Geometry is respected. Something so abstract, so mathematically intricate, is guiding you to a cafe, to a friend's house, to the quiet road home at night. And that contrast is worth lingering on. On one side, we have tensors, curved manifolds, equations dense enough to intimidate even physicists. On the other, we have ordinary life. Walking, driving, sleeping, and beneath every step, space-time curves gently around Earth. Beneath every ticking second, time flows at a rate determined by mass and motion. You do not feel it. You do not notice it, but you live inside it. If you imagine space-time not as a rigid structure but as something that responds softly to mass and energy, it begins to feel less like a grid and more like a slow breathing. Massive objects deepen the inhale, drawing curvature inward. Cosmic expansion stretches the exhale, lengthening the space between galaxies. It is not dramatic in daily life. The curvature around Earth is gentle. The slowing of time is subtle, but on larger scales, near stars, near neutron stars, near black holes, that breathing becomes deeper, heavier, more intense. And yet, the equations describing this behavior work with astonishing precision. On planetary scales, on galactic scales, in the bending of light, in the ticking of clocks, general relativity performs flawlessly. It is one of the most successful theories ever written. But as we drift further into this curved geometry, a quiet tension waits ahead, because there are places where the breathing becomes too deep, where curvature grows so extreme that the equations begin to tremble, places where relativity predicts infinities. We will move toward those places slowly. For now, just rest with this. Gravity is not a pull. It is the shape of the world around you, and every object, including you, is simply following the curves laid out by that shape. If we stay with this idea a little longer, something subtle begins to shift in how we picture motion itself. When you toss a ball upward and watch it arc back down, it feels natural to say gravity pulls it toward the ground. But in Einstein's picture, the ball is not being pulled in the way we once imagined. Instead, it is following the straightest possible path through a curved spacetime. That sentence can feel almost contradictory at first. How can something curve and still be straight? The answer lies in understanding that straight no longer means what it once did. In flat geometry, a straight line is the shortest distance between 2 points. In curved geometry, the straightest possible path is called a geodesic. It may appear curved to an outside observer, but within the geometry itself, it is the most natural, unforced motion available. So when the ball rises and falls, it is tracing a geodesic shaped by Earth's mass. The same is true for the moon circling Earth and for Earth circling the sun. They are not being yanked inward by invisible strings. They are moving along the curves written into spacetime by mass and energy. This is where the fabric analogy tries to help again. You imagine a heavy sphere pressing into a stretched sheet and smaller spheres rolling around it. But remember the limitation. The sheet bends because gravity pulls it downward in a higher dimension. Real spacetime does not rely on an outside pull. Its curvature is intrinsic. It does not dip into something else. It changes its own internal distances and durations. That difference matters because the bending is not just spatial. Time itself is part of the curvature. Imagine two observers, one standing at sea level and one on a mountaintop. From their own perspectives, nothing unusual is happening. Their hearts beat at normal rhythms. Their watches tick steadily. But if they compare clocks with sufficient precision, the one higher up will have aged slightly more. Time has passed faster there. The difference is minuscule, far beyond everyday awareness, yet atomic clocks reveal it clearly. The deeper you sit in a gravitational well, the slower time flows relative to someone higher up. This is not mechanical error. It is geometry breathing differently at different depths, and the effect grows stronger as gravity intensifies. Near a neutron star, where a mass greater than the sun is compressed into a sphere only tens of kilometers wide, time would slow dramatically compared to faraway space. Near a black hole, the slowing becomes extreme. To a distant observer, A clock approaching the event horizon appears to tick more and more slowly, its light stretched toward redder wavelengths, its moments thinning out as though diluted by curvature. Yet for the falling clock itself, time feels normal. This dual perspective is not illusion. It is built into the structure of spacetime. Different observers, moving differently or sitting at different depths in gravity, inhabit different slices of the same geometry. And still, in your daily life, everything feels steady. Floors do not sag noticeably beneath you. Seconds do not feel elastic. That emotional contrast is part of what makes relativity so quietly beautiful. Something unimaginably abstract is operating constantly beneath ordinary experience. Every orbit of every satellite, every trajectory of every spacecraft, every calculation of global positioning depends on these tiny differences in time and space. Engineers must account for both gravitational time dilation and the slowing of time due to high speed. Satellites orbit quickly, and motion itself also alters time. The combined corrections amount to microseconds per day, but without them, navigation systems would drift hopelessly. So each time your phone maps a route, it is quietly honoring the curvature of spacetime. If you let your imagination soften, you can picture the cosmos as a vast landscape whose shape is constantly adjusting. Massive galaxies create broad valleys. Stars carve smaller indentations. Planets create gentle dimples. Light flows along the contours, bending subtly around massive clusters. And all of this happens without friction, without sound, without resistance. The geometry does not strain, it simply adjusts, like a slow inhale and exhale across cosmic scales. On large scales, this breathing becomes even more dramatic. The universe itself is expanding, not exploding outward into empty space, but stretching internally. The distances between galaxies increase because space-time itself stretches. Imagine dots drawn on the surface of a balloon as it inflates. The dots move apart not because they crawl across the surface, but because the surface grows. In the same way, galaxies recede from each other because the geometry between them expands. That expansion is measurable through the redshift of distant light. Wavelengths stretch as space stretches. Time and space both participate in the same unfolding motion. And yet, for all this dynamism, general relativity remains astonishingly reliable on these scales. It predicts the precession of Mercury's orbit with exquisite accuracy. It predicts gravitational lensing, where entire galaxies act as lenses, bending light from objects behind them into arcs and rings. It predicts the slowing of time near massive bodies. It even predicts gravitational waves, ripples in spacetime generated when massive objects accelerate, such as two black holes spiraling together. Those waves have been detected, their patterns matching theoretical predictions almost perfectly. So here is the gentle tension forming beneath the calm surface. On large scales, relativity works beautifully. Planets, stars, galaxies, gravitational waves, cosmic expansion. The equations hold. The breathing geometry behaves exactly as described. But as curvature grows stronger and regions become smaller and denser, something begins to strain. When mass collapses far enough, The equations predict singularities, points where curvature becomes infinite, where density diverges without limit. Infinity is not something nature tends to allow quietly. It is often a sign that a theory has reached beyond its proper domain. So while space-time bends and time slows in ways we can measure and trust, there are edges where the breathing becomes too extreme, where geometry folds inward so tightly that our mathematical description begins to fray. We will move toward those edges soon. For now, let yourself rest inside the remarkable calm of it all. Gravity is shape, motion is path. Time is something that can stretch and soften depending on where you are in the cosmic landscape. There is something almost soothing about realizing that nothing in the universe is ever truly being yanked or shoved in the way our everyday language suggests. Instead, everything is following paths laid out by geometry. When you stand on the ground, you feel weight, but in this deeper picture, what you are really feeling is resistance. Your body is trying to follow a natural path through curved space-time, a path that would carry you inward toward the center of Earth. The ground prevents that motion. The pressure beneath your feet is not gravity pulling you down. It is the surface pushing you away from the geodesic you would otherwise follow. In orbit, astronauts feel weightless not because gravity has disappeared, but because they are freely following the curved geometry without resistance. They are falling continuously, yet never hitting the ground. That quiet redefinition changes everything. If you let that sink in slowly, gravity becomes less like a force and more like an environment. It is the shape of the room you are always inside. You do not see the walls of that room because they are not solid barriers. They are relationships between distances and durations. The presence of mass changes how far apart points are and how quickly moments pass. Even light, which does not experience time in the usual sense, still traces the curves. During eclipses, starlight grazing the sun bends just enough to shift its apparent position. That bending is small but precise. Entire galaxies can magnify distant background galaxies through gravitational lensing, creating luminous arcs that would not exist if space were flat. The images are not distortions in glass. They are distortions in geometry itself. Now imagine scaling this idea outward and inward at the same time. On the scale of planets and stars, the curvature is gentle. On the scale of galaxies, it becomes broader, shaping the motion of billions of stars at once. But as you move toward more compact objects, curvature deepens. A white dwarf compresses a star's mass into something the size of a planet. A neutron star compresses even further, squeezing more than the sun's mass into a sphere barely larger than a city. Their space-time is not merely dimpled. It is steep. Time slows noticeably relative to distant space. Light leaving the surface loses energy, stretched by the climb out of deep curvature. And then there are black holes. These are regions where collapse continues past any ordinary stopping point. According to general relativity, if enough mass gathers within a small enough volume, space-time curves so severely that a boundary forms. This boundary is called the event horizon. Inside it, every possible path leads further inward. Not even light can find a geodesic that escapes outward once it crosses that threshold. From far away, The horizon appears as a dark silhouette, but it is not a solid surface. It is a geometric condition, a place where the structure of spacetime tilts entirely inward. Approach that horizon, and something remarkable happens to time. To a distant observer, a clock falling toward the black hole appears to slow more and more. The signals it sends take longer to arrive. The light grows redder, fainter, stretched by the immense curvature. Eventually, it seems to freeze near the edge, never quite crossing. But from the viewpoint of the falling clock, nothing special occurs at that boundary. Crosses without drama, continuing inward. The disagreement between perspectives is not a trick. It is built into the geometry. Different observers carve spacetime into different slices of space and time. There is no single universal now binding them together. This is where relativity reveals both its elegance and its strain. The mathematics describing these curved regions is precise and powerful. Tells us exactly how horizons form, how light bends, how time dilates. But if you continue inward, toward the very center of a black hole, the equations predict something unsettling. Curvature grows without bound. Density rises toward infinity. Time and space, as described by the theory, collapse into a singular point where the mathematics can no longer proceed. Infinite curvature is not something we can measure. It is a signpost. It tells us the description has reached its limit. That limit does not show up in ordinary life. It does not disturb planetary orbits or the functioning of GPS satellites. On the scales we can test directly, relativity is flawless. Gravitational waves ripple through detectors exactly as predicted when massive black holes merge. The waves stretch and compress spacetime itself by tiny amounts, smaller than the width of a proton, yet measurable. These ripples confirm that geometry is dynamic, capable of oscillation. Spacetime is not rigid. It responds to motion, carrying information outward like the ringing of a bell. And still, at the deepest core of extreme curvature, something remains unresolved. The breathing of spacetime becomes too intense. The calm geometric picture predicts infinities, and infinities tend to signal that a theory is being asked to describe conditions beyond its proper domain. The same equations that describe the gentle curve around Earth and the dramatic warp around black holes with such precision also lead to breakdown when pushed too far. So we find ourselves in a quiet paradox. On large scales, relativity is astonishingly accurate. It explains light bending, time dilation, orbital motion, gravitational waves, cosmic expansion. It underlies technologies you use daily. It has passed every experimental test thrown at it for over a century. And yet, at singularities, at the deepest centers of collapse, it falters. The geometry it describes becomes too extreme, too tightly folded, for its own rules to handle. As we drift further into this curved landscape, that tension grows slightly more noticeable. The breathing of the cosmos remains gentle and predictable across stars and galaxies. But in the densest corners, something else must take over. The geometry we trust begins to hint that it is not the whole story. If we slow down here, right at the edge where relativity begins to strain, there is something almost poetic about the contrast. On the scales of planets and stars, the theory behaves like a perfectly tuned instrument. It predicts how Mercury's orbit shifts slightly over time. It predicts how clusters of galaxies bend light into luminous arcs. It predicts how time runs differently at different altitudes, how clocks in orbit must be corrected, how gravitational waves ripple outward when massive objects collide. Every one of these predictions has been confirmed with quiet precision. It is difficult to overstate how successful this geometric description has been. And yet, the very same equations, when asked to describe the deepest interiors of black holes or the earliest instance of the universe, deliver infinities. Not very large numbers, not extreme but finite quantities. Infinities, density without limit, curvature without bound. When physicists encounter infinities in equations that are meant to describe physical reality, they do not celebrate them. They treat them as warning signs. It is as though the mathematics is whispering that the map has reached the edge of its territory. To understand why this happens, imagine compressing matter further and further. As mass gathers into a smaller region, the curvature of spacetime deepens. The paths that objects can take tilt more steeply inward. Time slows more dramatically relative to distant observers. Keep compressing, and eventually, according to general relativity alone, there is no lower bound. The curvature increases endlessly as the radius shrinks towards zero. But nature rarely allows endless escalation without resistance. Other forces in physics tend to counterbalance extremes. Pressure resists compression in stars. Quantum effects resist certain kinds of collapse at microscopic scales. So when relativity predicts that curvature can become infinite, many physicists interpret that as a signal that another layer of physics must intervene before such an extreme is reached. The same tension appears if you run the cosmic story backward. Today, the universe is expanding. Galaxies drift apart as space-time stretches. But if you mathematically reverse that expansion, distances shrink. Galaxies move closer. Densities rise. Go far enough back, and the equations of general relativity again predict a singular beginning, a point of infinite density and curvature often associated with the Big Bang. Yet here, too, infinity suggests that the description is incomplete. It tells us that while relativity describes expansion beautifully, it may not fully capture the earliest conditions when everything was compressed into an unimaginably small region. So we stand in a curious place. On the one hand, space-time curvature is real, measurable, and reliable. On the other, its mathematical description breaks down under the most extreme conditions. The breathing geometry that feels so steady on large scales becomes too intense at singularities. The inhale collapses too deeply. The exhale cannot be traced back beyond a certain point. What makes this tension even more striking is how calmly it coexists with ordinary life. You wake up, walk across a room, check your phone for directions, and never once feel the curvature beneath you. The geometry is gentle, steady, predictable. The Earth's mass shapes spacetime just enough to hold oceans and atmosphere in place. The Sun's mass shapes spacetime just enough to keep planets in orbit. The galaxy's mass shapes spacetime just enough to keep stars bound in spirals. Everything seems harmonious, yet somewhere in the cosmos, two black holes spiral inward and merge. In that moment, curvature shifts violently. Spacetime rings with gravitational waves that travel across billions of light-years. By the time those waves reach Earth, they are faint, stretching detectors by tiny fractions of a proton's width. But they are measurable. They confirm that geometry is dynamic, elastic, responsive. The fabric analogy, imperfect though it is, hints at this elasticity. Massive objects do not just sit in spacetime. They move, and when they move, the curvature changes, sending ripples outward. Still, no experiment has ever directly observed the center of a black hole or the exact first instant of cosmic history. Those regions remain hidden behind horizons of one kind or another. The event horizon of a black hole blocks information from escaping. The cosmic horizon blocks light from regions too distant for signals to reach us since the universe began. In both cases, geometry sets boundaries on what can be known directly. This introduces a subtle emotional layer to the story. Spacetime is not only the structure that guides motion. It also limits perception. Its curvature defines not just how objects move, but what information can travel and where. Near a black hole, signals cannot escape. In the expanding universe, some galaxies recede so quickly due to the stretching of space that their light will never reach us. The geometry shapes not only trajectories, but horizons of knowledge. And so relativity remains both triumphant and incomplete. It triumphs across every scale we can test directly. It fails only where conditions become so extreme that another theory must take over. We do not yet know precisely what that deeper theory looks like. We only know that singularities and infinities mark places where the geometric description cannot be the final word. For now, though, you can rest inside the elegance of what does work. Gravity as curvature, motion as geodesic, time as something that flows at different rates depending on depth in a gravitational well. Light bending gently around stars, clocks ticking differently at different altitudes, GPS satellites adjusting for relativistic shifts, galaxies drifting apart as space stretches between them. All of it governed by a structure that never announces itself, yet quietly shapes every second of your life. And just ahead, waiting beyond the calm reliability of large-scale geometry, lies the deeper question: what happens when spacetime itself becomes too curved to describe? As we approach that question, it helps to pause and feel the contrast once more. For over a century, general relativity has described the large-scale universe with extraordinary grace. Planets trace stable paths. Stars orbit galactic centers. Light bends around massive clusters. Time slows in predictable ways near strong gravity. Even the faint ripples from distant black hole mergers align with the equations almost perfectly. There is a sense of harmony in that success, a sense that geometry, once understood as rigid and abstract, has become something alive and responsive, shaping reality at every scale we can comfortably observe. But harmony on large scales does not guarantee completeness at all scales. When curvature grows extreme, when matter compresses beyond neutron star densities, when the universe is imagined in its earliest fractions of a second, relativity signals distress. The infinities it predicts are not physical destinations we expect to encounter like mountains or valleys. They are markers that the map no longer corresponds to the terrain. Inside a black hole, the mathematics insists that spacetime curves inward without limit. Time and space swap roles in strange ways. Paths that once led outward now inevitably point toward the center. And at the very core, the equations predict a singularity, a region where curvature becomes infinite and known physics dissolves. Yet we do not truly believe that nature contains literal infinities in this way. Instead, we suspect that something new must intervene before that limit is reached. The same suspicion arises when thinking about the beginning of the universe. If you wind the cosmic clock backward, the expansion reverses. Galaxies converge, temperatures climb, densities rise. Eventually, relativity points to a state of infinite density and curvature. But just as with black holes, most physicists interpret this not as a final description, but as a boundary where the theory's jurisdiction ends. Something deeper must have governed that earliest state, something capable of describing spacetime under conditions where its curvature was unimaginably intense. So here is the gentle tension at the heart of this section. On scales of planets, stars, and galaxies, relativity works flawlessly. On scales of singularities, it breaks. It is not that gravity fails. It is that our geometric description reaches beyond what it can sustain. The breathing of spacetime, so calm and reliable in most regions, becomes too compressed at these extremes. The inhale tightens too sharply. The exhale cannot be traced back any further. And yet, while these extremes challenge theory, the ordinary world continues quietly under geometric guidance. When you stand, your body resists the inward geodesic that Earth's mass defines. When you look at distant starlight, it may already have bent slightly around intervening masses. When your phone calculates a route, it compensates for tiny relativistic shifts between orbiting satellites and the ground beneath you. None of this requires your awareness. The geometry operates silently. That emotional contrast is striking. On one side, unimaginable curvature at the cores of black holes. On the other, a person walking across a quiet room, unaware that time at their feet flows just slightly slower than time at their head. Something so abstract, so mathematically refined, is woven into each ordinary second. If you picture spacetime as a slow, cosmic breathing, most of the universe inhales and exhales gently. Galaxies drift apart as space expands. Massive objects create steady depressions in the geometry. Light follows curved contours without hesitation. But at singularities, the breathing becomes strained. Geometry folds inward too tightly. The smooth fabric image no longer suffices. It is here that relativity, despite its beauty, shows that it cannot be the final layer of reality. This realization does not diminish the theory. In fact, it highlights its strength. A framework capable of predicting light bending during eclipses, time dilation measured by atomic clocks, gravitational waves detected across billions of light years, and the precise corrections required for GPS satellites is not fragile. It is robust, but it is not absolute. It governs the large-scale curvature of spacetime with precision, yet it yields at the boundaries where curvature becomes infinite. And that boundary is where curiosity begins to stir more deeply. If spacetime bends and time slows, if gravity is geometry and geometry breathes, what happens when that breathing reaches its limits? What structure replaces smooth curvature when densities grow extreme? What description remains when infinities appear in equations meant to describe a physical world? We do not yet have those answers, but we know enough to recognize the pattern. Relativity governs the vast. It organizes the motion of galaxies and the flow of cosmic time. It describes a universe that bends gracefully under the presence of mass and energy. Yet at singularities, it gestures beyond itself, hinting that another framework must eventually take over. For now, rest in the quiet certainty of what is known. Gravity is not a force pulling you downward. It is the shape of spacetime guiding your path. Time does not flow identically everywhere. It responds to depth and motion. Light does not travel through an unchanging void. It follows curves carved by stars and galaxies. And every day, in ways too small to notice, these effects shape your life. The cosmos breathes slowly through curvature. Most of that breathing is gentle, steady, and beautifully predictable. Only at the deepest compressions does it strain. And it is in those strained regions that the next layer of understanding waits. If you're still here with me, still drifting through curved geometry, type 1 in the comments. There is a quiet fracture running beneath our understanding of reality. Not a crack you can see in the night sky, not a tremor you can feel under your feet, but a tension hidden in the mathematics that describes the universe. On one side of this fracture stands general relativity, calm and geometric, describing spacetime as a smooth, continuous structure that bends gently around stars and galaxies. On the other side stands quantum mechanics, restless and probabilistic, insisting that nothing at the smallest scales is ever perfectly still, perfectly defined, or perfectly smooth. Both theories work. Both predict experimental results with astonishing precision. And yet, when they are asked to speak about the same place at the same time, they begin to disagree. Relativity paints spacetime like a seamless landscape. Imagine an endless terrain without seams or grains, curving gradually wherever mass and energy gather. Planets follow natural paths through that curvature. Light bends as it passes near stars. Time itself slows in stronger gravitational fields. The equations of relativity describe this geometry with extraordinary accuracy. When gravitational waves ripple across the cosmos, detectors confirm exactly what the theory predicted. When atomic clocks are lifted higher above Earth's surface, they tick slightly faster, just as relativity says they should. On large scales, the universe behaves like a smooth fabric breathing slowly under the weight of galaxies. Quantum mechanics tells a very different story. At the smallest scales, the universe refuses to sit still. Particles do not have precise positions and velocities at the same time. Instead, they are described by wave functions, mathematical expressions of probability. Particle is not here or there until it is measured. It exists as a spread of possible locations. Energy is not constant in the quiet sense we imagine. Even in empty space, tiny fluctuations flicker in and out of existence. Fields vibrate. Virtual particles briefly appear and vanish. Uncertainty is not a flaw in measurement. It is woven into the rules themselves. Now imagine trying to place these two descriptions on top of each other. Relativity requires a smooth stage, a continuous geometry where every point connects gently to the next. Quantum mechanics insists that at very small scales, fluctuations are unavoidable. If everything fluctuates, then space-time itself should fluctuate. It should jitter with microscopic turbulence. But relativity does not allow that. Its geometry is precise. Its curvature is defined at every point. The smoothness is essential. This contrast becomes more dramatic when you consider vacuum energy. Quantum theory predicts that even empty space is not truly empty. Instead, it is filled with fluctuations of energy. If you calculate the expected energy density of this quantum vacuum using standard methods, the result is enormous. Not slightly too large, not moderately off, enormous beyond ordinary imagination. The predicted value is larger than what we observe by a factor of about 10 raised to the power of 120. That is a 1 followed by 120 zeros. It is often described as the largest mismatch between theory and observation in the history of physics. Relativity tells us that energy curves space-time. If empty space truly contained the immense vacuum energy that quantum mechanics predicts, space-time would curve so violently that the universe would either collapse immediately or expand at an unimaginable rate. But it does neither. The observed expansion of the universe is gentle enough to allow galaxies, stars, and planets to form. Something is canceling out almost all of that predicted vacuum energy, or our understanding of how vacuum energy interacts with gravity is incomplete. The two frameworks, each accurate in isolation, collide here with stunning disagreement. This is not a small technical issue. It is a sign that the foundations beneath our theories do not align perfectly. And yet the universe itself remains stable, consistent, coherent. The fracture exists in our description, not in reality. The disagreement grows sharper in the presence of extreme gravity. Black holes offer the most dramatic example. According to general relativity, when a massive star collapses under its own gravity, space-time curves inward more and more steeply. If the collapse continues without interruption, the equations predict a singularity at the center, a point of zero volume and infinite density, infinite curvature, infinite gravitational pull. In mathematical language, certain quantities diverge without limit. Infinity in physics is rarely a comfortable result. It usually signals that a theory has been pushed beyond its domain of validity. Relativity handles the outer regions of a black hole beautifully. It predicts the shape of the event horizon, the bending of light, the slowing of time near the boundary. All of these predictions have been confirmed through observation. But at the exact center, The singularity forms like a warning light. The mathematics stops giving meaningful answers. Quantum mechanics, on the other hand, does not tolerate such infinities. Its structure depends on probabilities that remain finite and well-behaved. If matter is compressed to extremely small scales, quantum effects should become dominant. Uncertainty principles prevent particles from being confined to arbitrarily small regions without enormous energy fluctuations. In principle, quantum mechanics should resist the formation of an infinitely dense point. Yet we do not have a complete quantum theory of gravity. We cannot fully describe what happens inside a black hole where both curvature and quantum uncertainty are equally important. Relativity predicts a singularity. Quantum reasoning suggests that something else must occur before infinity is reached. But without a unified framework, we cannot say what replaces the singularity. A dense quantum state? A new phase of spacetime? A bounce into another region? The theories fall silent at the exact place where their cooperation is most needed. Then there is the information paradox. In quantum mechanics, information about a system is never truly destroyed. The evolution of a quantum system is governed by equations that preserve information over time. Even if particles scatter or transform, the underlying information remains encoded in correlations. But in classical general relativity, if an object falls into a black hole and crosses the event horizon, the details of its internal structure appear to vanish from the observable universe. The black hole is described by only a few properties: mass, charge, and spin. All other information seems erased. This conflict creates deep tension. If black holes truly destroy information, quantum mechanics would need revision. If information is preserved, then relativity's description of black holes is incomplete. Decades of research have suggested that information might be encoded subtly in the radiation emitted by black holes, known as Hawking radiation. Over immense timescales, black holes slowly evaporate through quantum effects near the event horizon. If the radiation carries away information in a highly scrambled form, then perhaps nothing is truly lost. But the details remain under debate. The paradox persists as a reminder that our frameworks do not yet fit together cleanly. And still, both theories are astonishingly successful. Quantum electrodynamics predicts experimental results to many decimal places of accuracy. Relativity predicts gravitational lensing, time dilation, and gravitational waves with equal precision. They are not weak or approximate models. They are pillars of modern science. The fracture does not arise because either one fails in its own domain. It arises because reality spans domains where both must apply at once. This coexistence of accuracy and incompatibility is one of the most humbling features of modern physics. The universe behaves consistently. Our descriptions are the ones struggling to merge. Beyond black holes, other gravitational clues deepen the mystery. Galaxies rotate in ways that cannot be explained by visible matter alone. Stars at the outer edges of galaxies move too quickly. According to relativity, the curvature of spacetime around a galaxy depends on its mass. But when astronomers measure the mass we can see, The predicted curvature is too small to hold those fast-moving stars in orbit. Something else must be contributing additional gravity. This unseen component is called dark matter. It does not emit light. It does not absorb light. It does not appear to interact through electromagnetic forces at all. Yet its gravitational influence shapes galaxies, clusters, and the large-scale web of cosmic structure. Relativity describes how dark matter curves spacetime, but it does not tell us what dark matter is made of. Quantum mechanics describes particles and fields, but no confirmed particle yet matches the required properties. The presence of dark matter suggests that our inventory of the universe is incomplete. Dark energy presents a different kind of gravitational puzzle. Observations of distant supernovae and the large-scale structure of the cosmos reveal that the expansion of the universe is accelerating. Spacetime itself is stretching faster over time. In the equations of relativity, this behavior can be represented by a term that acts like a uniform energy density filling space. But the nature of that energy remains unknown. It behaves like a property of the vacuum, exerting a kind of negative pressure that drives expansion. Here again, the tension with quantum predictions appears. The measured value of dark energy is tiny compared to the enormous vacuum energy predicted by naive quantum calculations. Somehow, the effective vacuum energy that influences cosmic expansion is extremely small but not exactly zero. Why it has that specific value remains one of the deepest unsolved problems in physics. Dark matter and dark energy together make up roughly 95% of the total energy content of the universe. Ordinary matter, stars, planets, gas, dust, everything we see, accounts for only a small fraction. That means most of the gravitational behavior shaping spacetime comes from components we do not yet understand. Relativity describes their effects flawlessly once their densities are inserted into the equations. But the underlying explanation remains elusive, and so the picture becomes layered. At large scales, spacetime curves smoothly according to relativity. At small scales, quantum fields fluctuate with uncertainty. In between, we encounter black holes, cosmic expansion, dark matter halos, and vacuum energy discrepancies. Each piece functions within its own framework. Together, they hint at a deeper unity not yet uncovered. Some physicists have begun to consider whether spacetime itself might not be the most fundamental ingredient. Perhaps the smooth geometry described by relativity is an emergent phenomenon, arising from underlying quantum relationships. In certain theoretical models, patterns of quantum entanglement, the deep correlations between particles, appear to give rise mathematically to geometric structures resembling spacetime. Distance, in these models, reflects the strength of quantum connections rather than a pre-existing stage. If this idea holds truth, then spacetime might be similar to temperature. Temperature feels fundamental in everyday life, yet it emerges from the collective motion of microscopic particles. In the same way, curvature and geometry might emerge from deeper quantum interactions. The smooth fabric would then be a large-scale approximation, valid when many underlying elements combine in coherent ways. This possibility does not diminish relativity. It explains why relativity works so beautifully at macroscopic scales. It simply suggests that beneath the smoothness lies a more granular or relational structure. The fracture between relativity and quantum mechanics might then reflect our attempt to treat an emergent layer as fundamental. If spacetime is emergent, the contradictions between smooth curvature and quantum uncertainty may not be contradictions at all, but signs of scale. At large distances and low energies, fluctuations average out. Geometry appears continuous. At extremely small scales, the averaging breaks down. The underlying discreteness or network of relations becomes dominant. Our current equations may describe each limit correctly while failing in the transition region between them. Even without committing to any specific theory, the emotional picture becomes clearer. The universe itself does not flicker between two rulebooks. It follows one consistent reality. Our frameworks are partial windows into that consistency. Each window shows a different aspect, shaped by the scale at which we observe. There is a certain calm in recognizing this. The fracture beneath reality is not chaos. It is incompleteness. The universe does not contradict itself. Only our current descriptions struggle to unify the whole. When you look at the night sky, you see stars bound in galaxies by gravity. You see light that has traveled billions of years through expanding spacetime. You see patterns shaped by dark matter halos and accelerated by dark energy. At the same time, every atom in your body follows quantum rules, governed by probabilities and uncertainty principles. Both descriptions are true. Both are operating right now quietly without conflict in the physical world. The tension exists only in our mathematics. It is as if we have two maps of the same terrain, each exquisitely detailed, each accurate within its boundaries, but drawn using different coordinate systems. Where the maps overlap, the lines do not align perfectly. That misalignment invites deeper exploration. Perhaps future theories will reveal that geometry and quantum information are two expressions of a single underlying principle. Perhaps spacetime will be understood not as a static backdrop, but as a dynamic layer emerging from relationships. Perhaps the vacuum energy puzzle will find resolution in a symmetry not yet recognized. We cannot say, but the pattern of history suggests that contradictions at the boundaries of knowledge often signal approaching insight. The fracture beneath reality is therefore not a failure. It is a frontier. It marks the place where understanding has reached its current edge. Beyond that edge lies a description more unified, more subtle, and perhaps more surprising than either relativity or quantum mechanics alone. And so we rest in a universe that works flawlessly, even while our explanations continue to evolve. The stars do not hesitate because our equations disagree. Black holes do not pause at singularities. Dark energy does not wait for clarification. The cosmos unfolds with steady consistency. We are the ones still stitching our frameworks together. As the night deepens and your thoughts grow softer, it can be comforting to hold onto this simple idea. The universe is not fractured. Our models are. The smooth curves of relativity and the shimmering uncertainties of quantum mechanics are not enemies. They are partial reflections of a deeper order that remains just beyond full articulation. Space-time may not be the final layer. It may. There is a quiet fracture beneath our understanding of reality, not a visible crack in the sky, not a tremor under the ground, but a tension hidden in the mathematics that describes the universe. On one side stands general relativity, calm and geometric, presenting space-time as a smooth, continuous structure that bends gracefully around stars and galaxies. On the other side stands quantum mechanics, restless and probabilistic, insisting that at the smallest scales nothing is ever perfectly still or perfectly certain. Both theories are extraordinarily successful. Both predict experimental results with astonishing precision. And yet, when they are asked to describe the same extreme conditions at the same time, they refuse to agree. Relativity paints space-time as seamless. Imagine an endless landscape without seams or grains, curving gently wherever mass and energy gather. Planets follow natural paths through that curvature. Light bends as it passes near massive objects. Time itself slows in stronger gravitational fields. The equations describe this geometry with exquisite accuracy. Gravitational waves ripple across the cosmos exactly as predicted. Atomic clocks tick at slightly different rates depending on altitude, matching calculations down to tiny fractions of a second. On large scales, the universe behaves like a smooth fabric breathing slowly under the weight of galaxies. Quantum mechanics tells a very different story. At the smallest scales, the universe does not remain smooth. Particles do not have definite positions and velocities simultaneously. Instead, they are described by probabilities. A particle exists as a spread of possible outcomes until measured. Even empty space is not empty. Fields fluctuate. Tiny bursts of energy appear and disappear. Uncertainty is not a limitation of our tools. It is built into the structure of reality at microscopic levels. Now imagine trying to place these two pictures on top of each other. Relativity requires smoothness. Its geometry depends on precise curvature defined at every point. Quantum mechanics insists that at very small scales fluctuations are unavoidable. If everything fluctuates, then space-time itself should fluctuate. It should jitter with microscopic turbulence. But relativity does not allow that. Its equations assume a continuous background. This tension becomes overwhelming when we examine vacuum energy. Quantum theory predicts that empty space contains energy due to constant fluctuations. When physicists calculate the expected energy density of this quantum vacuum, the result is staggering. It is larger than what we observe in the real universe by a factor of 10 raised to the power of 120. That is a 1 followed by 120 zeros. It is often called the greatest mismatch in the history of physics. Relativity tells us that energy curves space-time. If empty space truly contained that enormous energy density, space-time would curve violently. The universe would either collapse immediately or expand at an unimaginable rate. But it does neither. Instead, the observed expansion of the universe is gentle enough to allow galaxies and stars to form. Something is canceling out almost all of that predicted vacuum energy, or our understanding of how vacuum energy interacts with gravity is incomplete. The fracture is not subtle. It is immense, and yet the universe itself remains calm and coherent. The tension exists in our descriptions, not in reality. The cosmos does not flicker between two rulebooks. It follows one consistent set of laws we have not yet unified. Relativity works perfectly when describing planets, stars, galaxies, and gravitational waves. Quantum mechanics works perfectly when describing atoms, particles, and electromagnetic interactions. Both are astonishingly accurate. The problem arises only when we push them into the same extreme environment, where curvature is intense and scales are microscopic. That place, where smooth geometry and quantum uncertainty collide, marks the deepest fracture beneath our current understanding of spacetime. The fracture becomes even more dramatic when gravity grows extreme, and nowhere is gravity more extreme than inside a black hole. According to general relativity, when a massive star collapses under its own weight, spacetime curves inward more and more steeply. If nothing stops the collapse, the equations predict a singularity at the center, a point where density becomes infinite and curvature becomes infinite. Infinite means the mathematics no longer produces sensible physical quantities. It is not simply very large. It is unbounded. Whenever infinity appears in physics, it usually signals that a theory has been pushed beyond the conditions where it can safely operate. Relativity describes the outer structure of black holes beautifully. It predicts the size of the event horizon, the way light bends around it, the way time slows dramatically near the boundary. All of these predictions have been confirmed through observation. But at the very center, the equations reach a breaking point. Quantum mechanics refuses to accept infinities like this. At extremely small scales, uncertainty principles prevent matter from being compressed without limit. If you try to confine a particle into an extremely tiny region, its momentum uncertainty increases, and with it the energy associated with that uncertainty. Quantum effects should become overwhelmingly important before infinite density is reached. Yet we do not possess a complete theory that unites quantum mechanics with gravity. We cannot fully describe what happens at the center of a black hole where both quantum effects and extreme curvature are essential. Relativity predicts a singularity. Quantum reasoning suggests that something else must occur before infinity is allowed. But without a unified framework, we are left with a question mark at the heart of one of the universe's most powerful objects. This tension extends to the information paradox. In quantum mechanics, information is preserved. The equations governing quantum evolution ensure that the full description of a system remains encoded in its state over time. Information may become scrambled, spread out, or incredibly difficult to reconstruct, but it is not destroyed. In classical general relativity, if something falls into a black hole and crosses the event horizon, all detailed information about its internal structure appears to vanish from the observable universe. The black hole can be described only by its mass, charge, and spin. Everything else seems erased. This apparent destruction of information conflicts directly with quantum theory. To resolve this, physicists proposed that black holes are not entirely black. Quantum effects near the event horizon allow them to emit a faint radiation, now known as Hawking radiation. Over immense periods, black holes slowly lose mass and can eventually evaporate. The crucial question is whether the radiation carries away the information that fell inside, encoded in an extremely subtle way. If it does, quantum mechanics remains intact, but relativity's classical description is incomplete. If it does not, quantum theory must be revised. Decades of work have suggested that information is likely preserved, but the full mechanism is still debated. Once again, both frameworks are individually powerful and accurate, yet they resist merging into one coherent description in extreme conditions. Meanwhile, outside black holes, further gravitational clues hint at missing pieces. Galaxies rotate faster than they should if only visible matter were present. According to relativity, the curvature of spacetime around a galaxy depends on its mass. When astronomers measure the mass we can see, the predicted gravitational pull is insufficient to keep the outer stars moving at their observed speeds. Something unseen must be contributing additional gravity. This invisible component is called dark matter. It does not emit light or interact electromagnetically in any detectable way. Yet its gravitational influence shapes galaxies and clusters. Relativity describes how dark matter curves spacetime once its presence is assumed, but it does not reveal what dark matter actually is. Quantum mechanics describes particles and fields with extraordinary success, yet no confirmed particle fits the required profile of dark matter. The presence of dark matter indicates that our understanding of the universe's content is incomplete. The fracture beneath reality is not only about singularities and paradoxes. It also appears in the unseen mass shaping the cosmos. The universe behaves consistently. Our frameworks, however, are still searching for the deeper structure that makes all these pieces align without contradiction. Beyond dark matter, there is an even more subtle gravitational clue that deepens the fracture in our understanding, and that clue is dark energy. Observations of distant supernovae, combined with measurements of the cosmic microwave background and the large-scale distribution of galaxies, reveal something unexpected. The expansion of the universe is accelerating. Space-time is not merely stretching. It is stretching faster over time. Within the framework of general relativity, this behavior can be described by including a term in the equations that acts like a uniform energy density filling all of space. This energy has a peculiar property often described as negative pressure. Instead of pulling spacetime inward the way normal matter does, it pushes spacetime outward, driving accelerated expansion. Yet while the mathematics can accommodate this effect, the nature of dark energy remains unknown. It behaves like a property of empty space itself. And once again, the tension with quantum predictions appears. Quantum field theory predicts vacuum energy from constant microscopic fluctuations. But as described earlier, the predicted value is incomprehensibly larger than what cosmological observations allow. The actual measured density of dark energy is tiny compared to naive quantum calculations. Somehow, almost all of the expected vacuum energy is cancelled or neutralized, leaving behind only a small residual effect that drives cosmic acceleration. Why that cancellation occurs, and why the leftover value has precisely the magnitude it does, is one of the deepest open questions in theoretical physics. If the vacuum energy were slightly larger, the universe would have expanded too rapidly for galaxies to form. If it were slightly smaller or negative, gravity might have reversed the expansion long ago. The balance appears delicately tuned, and neither relativity nor quantum mechanics alone explains why. When we step back, the scale of incompleteness becomes striking. Ordinary matter, the stars, planets, gas, and dust we see, makes up only a small fraction of the total cosmic energy budget. Dark matter and dark energy together dominate the gravitational behavior of the universe. Relativity describes how these components curve spacetime once their densities are inserted into the equations. But the equations themselves do not tell us what these components fundamentally are. Quantum theory, meanwhile, offers a framework for describing particles and fields, yet has not delivered confirmed candidates that fully account for these phenomena. The universe behaves in a coherent and stable way, but most of what shapes its geometry remains mysterious. This deepens the emotional tone of the fracture. It is not that physics is failing. It is that our current layers of description are incomplete. Each theory captures a different scale. Relativity governs the smooth curvature of spacetime on large scales. Quantum mechanics governs the probabilistic behavior of fields and particles on small scales. Cosmology bridges vast distances and early times. But when these layers overlap, contradictions emerge. It begins to suggest that spacetime itself might not be the most fundamental layer of reality. Some physicists have proposed that spacetime could be emergent, meaning that it arises from deeper quantum relationships rather than existing as the ultimate foundation. In certain theoretical models, patterns of quantum entanglement appear to generate geometric structures mathematically similar to curved spacetime. In these pictures, distance is not a primitive ingredient but a measure of how strongly quantum states are correlated. Stronger entanglement corresponds to closer effective distance. Weaker entanglement corresponds to greater separation. Geometry becomes a manifestation of information relationships. If this idea contains truth, then the smooth spacetime described by relativity would be analogous to temperature. Temperature feels fundamental in daily life, yet it emerges from the collective motion of countless microscopic particles. No single particle has temperature on its own. Similarly, spacetime might emerge from a vast network of underlying quantum interactions. At large scales, those interactions average out into smooth geometry. At extremely small scales, the averaging breaks down, and the smooth picture dissolves into something more granular or relational. This perspective offers a way to soften the fracture. Instead of viewing relativity and quantum mechanics as incompatible rivals, they could be understood as effective descriptions operating at different levels of emergence. Relativity would describe the large-scale behavior of an emergent geometry. Quantum mechanics would describe the deeper substrate from which that geometry arises. The conflict appears only when we attempt to push either framework beyond its natural domain. The universe itself remains consistent. Stars still orbit galactic centers shaped by unseen mass. Spacetime continues expanding under the influence of dark energy. Atoms in your body obey quantum rules without hesitation. The fracture is not in the cosmos. It is in our attempt to compress the full richness of reality into a single layer of explanation before we have uncovered the deeper structure that unifies them all. If space-time is not fundamental but emergent, then the deepest fracture beneath reality may not be a crack at all, but a boundary between layers of description. This idea does not weaken general relativity. On the contrary, it explains why relativity works so beautifully in the domain where smooth geometry dominates. When you average over enormous numbers of microscopic interactions, the jagged details disappear. What remains is curvature that looks continuous and calm. Planets follow geodesics. Light bends around massive bodies. Time slows in gravitational wells. All of these effects emerge naturally if spacetime behaves like a large-scale pattern arising from deeper processes. At the same time, quantum mechanics would not be trying to bend a smooth background at all. It would be describing the underlying structure from which that background arises. The tension appears only when we assume that both theories are speaking about the same fundamental layer in the same way. Consider again the vacuum energy problem. Quantum field theory calculates enormous zero-point energy because it sums contributions from fluctuations at every possible frequency. But those calculations assume a fixed spacetime background. If spacetime itself is part of the system that responds dynamically to those fluctuations, then the naive calculation might not apply in the way we expect. The huge predicted value could be an artifact of treating geometry as passive when it is not. Perhaps the underlying theory automatically cancels most of the vacuum energy once spacetime is allowed to participate in the dynamics at the same level as quantum fields. In that case, the enormous mismatch would not signal a catastrophic failure, but a clue that our separation between geometry and quantum fluctuations is artificial. The same layered interpretation might soften the singularity problem. When relativity predicts infinite curvature, it is extrapolating smooth geometry into a regime where smoothness may no longer exist. If spacetime has a discrete or relational microstructure, then at sufficiently small scales the concept of continuous curvature breaks down. Infinity appears only because we are forcing a continuous description beyond its valid range. In a deeper theory, the collapse of matter inside a black hole might approach a maximum density determined by the microscopic structure of spacetime, avoiding true singularities. What looks like an infinite spike in curvature would be replaced by a new phase of geometry governed by quantum rules. The information paradox may also appear differently in this light. If spacetime geometry and quantum information are intertwined at a fundamental level, then the boundary of a black hole might encode information not as a classical surface but as part of the quantum fabric that generates spacetime itself. Information would never leave the deeper layer. It would remain within the relational structure from which both geometry and matter arise. From this perspective, information is not traveling through spacetime in the ordinary sense. It is part of the network that gives spacetime meaning. Dark matter and dark energy, too, could reflect limitations of our current layer. Dark matter might not be an invisible particle in the traditional sense. It might represent new degrees of freedom in the underlying structure that manifest gravitationally at large scales. dark energy might not be a mysterious fluid filling space, but a reflection of how the deeper layer sets the large-scale curvature of the emergent geometry. In each case, what we label as missing components could instead be signals that spacetime is not the bedrock, but the surface. This way of thinking requires patience. It does not provide immediate answers. It does not supply a finished equation that unifies everything cleanly, but it changes the emotional texture of the fracture. Instead of a contradiction that threatens the coherence of physics, the incompatibility between relativity and quantum mechanics becomes a signpost. It tells us that we are working with effective theories that describe different scales accurately, yet neither reaches all the way down. The universe itself shows no sign of confusion. Gravitational waves propagate smoothly across billions of light years. Quantum interference patterns appear reliably in laboratories. Cosmic expansion follows consistent laws. The coherence of reality is not in doubt. Only our framework is incomplete. The fracture beneath reality is therefore quiet. It does not tear the cosmos apart. It simply marks the place where understanding transitions from known structure to deeper possibility. We stand at that boundary, aware that smooth spacetime and quantum uncertainty are both real features of our descriptions, yet sensing that they may be two shadows cast by a single, more fundamental light we have not yet fully seen. When you step back from the equations, from the infinities and mismatches and paradoxes, a quieter picture begins to form. The universe itself has never once hesitated. Stars ignite, galaxies rotate, black holes merge, spacetime expands. At the smallest scales, particles interfere and entangle with flawless consistency. The fracture exists only in our attempt to compress all of that behavior into a single explanatory frame before we have discovered the deeper structure that holds it together. Relativity describes a smooth geometric world where curvature guides motion. Quantum mechanics describes a probabilistic world where uncertainty is fundamental. Both descriptions are astonishingly precise within their domains. The fact that they resist unification does not mean one is wrong. It means reality is richer than either alone. There is something deeply humbling about that realization. For centuries, physics advanced by unifying apparently separate phenomena. Electricity and magnetism became electromagnetism. Space and time merged into spacetime. Matter and energy were shown to be interchangeable. Each step brought greater simplicity at a deeper level. Now we stand at another threshold. Gravity and quantum theory remain separated not by lack of effort, but by conceptual tension. Smooth continuity clashes with microscopic fluctuation. Deterministic geometry meets probabilistic amplitude. Infinities appear where the frameworks overlap. Yet instead of chaos, what we see is coherence beyond our current reach. The universe behaves as though a single consistent set of rules operates everywhere. We simply do not yet possess the language capable of expressing that unity fully. Dark matter and dark energy remind us that most of what shapes spacetime is invisible to direct detection. Singularities remind us that pushing smooth geometry too far produces mathematical warnings. The vacuum energy mismatch reminds us that naive calculations can overshoot reality by inconceivable margins. The information paradox reminds us that our understanding of time, causality, and entropy may still be incomplete. None of these puzzles indicate disorder in nature. They indicate boundaries in theory. And boundaries are not failures. They are invitations. It is possible that spacetime, which feels so fundamental, is itself a layer emerging from deeper relationships. If so, then smooth curvature and quantum uncertainty are not enemies but complementary aspects of a larger pattern. At vast scales, the pattern expresses itself as geometry. At tiny scales, it expresses itself as probability and fluctuation. The incompatibility arises only when we insist on treating one layer as the foundation of the other. Perhaps the true foundation is something more abstract, a network of relations, a structure of information, a principle that gives rise simultaneously to curvature and uncertainty. We do not yet know. What we do know is that every experiment continues to confirm the internal consistency of both relativity and quantum mechanics in their respective domains. The universe does not flicker between smooth and jittery behavior at random. It transitions seamlessly across scales. That seamlessness suggests an underlying coherence we have not fully articulated. There is something almost comforting in recognizing that our incompleteness does not threaten reality itself. The cosmos remains stable while we refine our models. The stars will continue to orbit galactic centers shaped by unseen mass. Space will continue to stretch under the influence of dark energy. Particles will continue to obey quantum laws with unwavering reliability. The fracture beneath reality is therefore not a crack in existence. It is a gap in comprehension, and gaps in comprehension are natural in any evolving field of knowledge. Each paradox sharpens the questions. Each mismatch narrows the possibilities. Each failed unification attempt teaches us what cannot be true, bringing us incrementally closer to what might be. There is quiet beauty in that process. We are not outside the universe looking in. We are part of the structure trying to understand itself. The very quantum fields and curved spacetime we study are the same ingredients that form our minds. The tension between theories is not a cosmic error. It is a stage in the unfolding of understanding. And so we rest tonight inside a universe that is internally consistent even if our equations are not yet unified. Smooth spacetime and quantum uncertainty coexist without contradiction in nature. The fracture lies only in the language we use to describe them. If you're still listening, still awake somewhere in this vast structure, type 2 in the comments. There is a quiet possibility that changes everything without disturbing a single star in the sky. It is the possibility that spacetime, the vast, bending structure that holds galaxies, carries light, and stretches with cosmic expansion, is not the deepest layer of reality. That it may be real, measurable, and powerful, yet still not fundamental. To sense what that means, think about temperature. Temperature feels basic. You step outside and feel cold air on your skin. You warm your hands around a cup and feel heat rising into your fingers. Temperature seems like a primary feature of the world. But if you zoom in far enough, temperature disappears. A single molecule has no temperature. Only when countless particles move together does temperature emerge as a collective behavior. It is not a building block. It is a large-scale effect. Now imagine spacetime in the same way. The smooth curves described by relativity. The slowing of clocks near massive objects. The stretching between galaxies as the universe expands. All of these behaviors might be like temperature, the large-scale appearance of something deeper moving beneath the surface. If that is true, then asking what spacetime is made of becomes like asking what temperature is made of. The answer would not be threads or fabric. It would be relationships, interactions, perhaps even information. This idea has grown stronger over the past few decades, especially when scientists began studying black holes more carefully. Black holes, those regions where curvature becomes extreme, revealed something unexpected about entropy, a measure of information. When physicists calculated the entropy of a black hole, they found that it was proportional not to its volume, but to the area of its surface. That detail is subtle but astonishing. In ordinary objects, the amount of information you can store grows with volume. A larger box holds more than a smaller one because it has more interior space. But black holes defy that intuition. Their informational capacity scales with surface area. That hint suggests something radical. It suggests that the three-dimensional interior might somehow be encoded on a two-dimensional boundary. Not in a science fiction sense, but in a mathematical one. The geometry we experience could be a projection of deeper informational structures. If that were true, spacetime would not be the ultimate stage. It would be an emergent display arising from something encoded elsewhere. There is a calm elegance to this possibility. It would explain why attempts to quantize gravity directly produce infinities. Perhaps we are trying to quantize something that is not fundamental. It would also explain why quantum entanglement seems indifferent to distance. If geometry arises from entanglement patterns, then entanglement would not occur inside spacetime. It would help generate spacetime itself. Imagine two particles deeply entangled. Their states linked so completely that measuring one immediately constrains the other. If entanglement were the thread from which geometry is woven, then strong entanglement would correspond to short distances. Weak entanglement would correspond to greater separation. In this view, distance is not primary. Connection is. Geometry becomes a map of informational relationships. This might sound abstract, but there is something gently intuitive about it. In daily life, closeness is not only spatial. Two people far apart can feel deeply connected. Two objects sitting side by side can feel unrelated. The universe, at its deepest level, may measure closeness by correlation rather than meters. If enough correlations interlock in specific patterns, the smooth curves of spacetime could emerge the way a coastline emerges from countless grains of sand. Other approaches explore this idea differently. Some suggest that spacetime may be built from discrete elements, tiny indivisible units far smaller than atoms. Instead of a continuous fabric, there could be a fine structure, a network of nodes and links. At large scales, that network would look smooth, just as a digital photograph looks continuous from far away. But up close, it would resolve into pixels. In loop-based models of quantum gravity, space is woven from loops of fundamental area. These loops connect in intricate patterns, forming a granular structure. Time, in such pictures, does not flow smoothly but progresses through transitions between configurations. Smooth geometry would be an approximation valid only when the loops are numerous and densely connected. The infinities predicted by classical relativity would never arise because the smallest units would impose natural limits. There is something quietly reassuring about discreteness. It suggests that the universe has a smallest meaningful scale, beyond which questions like "what is smaller than this?" simply lose meaning. It would mean that singularities, those infinite densities predicted at black hole centers, are not real infinities, but artifacts of applying smooth mathematics where smoothness no longer exists. At the same time, the universe continues expanding. Galaxies drift apart as space-time stretches between them, and that expansion is accelerating. Something we call dark energy is causing the stretching to speed up. If space-time is emergent, then perhaps dark energy is not an added ingredient. Perhaps it reflects properties of the deeper layer from which space-time arises. Maybe the underlying informational structure favors expansion, the way heated air naturally expands when energy increases microscopic motion. Cosmic horizons add another layer to this reflection. Because space expands and light travels at a finite speed, there are regions of the universe forever beyond our view. The observable universe has an edge defined not by matter but by causality. Beyond that horizon lie galaxies whose light will never reach us. If geometry itself is emergent, then even that horizon might represent a boundary in information flow rather than a boundary in physical substance. Inflation, the rapid expansion believed to have occurred in the earliest fraction of a second, may also hint at emergence. During inflation, space-time expanded exponentially, smoothing irregularities and setting the stage for cosmic structure. But inflation itself likely arose from a field with specific properties. That field may have been connected to quantum fluctuations, amplified to cosmic size. The geometry we see today could therefore carry imprints of microscopic processes stretched across billions of light years. All of these ideas point in a similar direction. Space-time might not be the canvas. It might be the painting, and beneath the painting could be patterns of interaction, entanglement, or information that do not resemble space or time at all. The future of physics may depend on learning to describe reality without assuming geometry at the outset. Instead of starting with space and placing objects inside it, theories may begin with relationships and allow space to arise later. Instead of assuming time flows and events occur within it, time itself may emerge from changes in entanglement or from the growth of complexity. As we drift further into this possibility, the sharp edges of certainty soften. The universe does not feel less real, feels deeper. The stars still shine. Gravity still guides planets in their paths. Clocks still tick. But beneath those familiar rhythms may lie a quieter layer where geometry is not fundamental, where distance is a shadow of connection, and where the smooth stage of space-time is a large-scale appearance of something more subtle and more profound. And if that is true, then we are not merely living in spacetime. We are living in the emergent surface of a deeper reality that has yet to fully reveal itself. If spacetime is not fundamental, then what becomes fundamental instead is not a surface or a direction, but structure in a quieter sense. Not structure as in shape, but structure as in pattern. Many modern approaches lean toward the idea that information, the yes or no of physical states, the arrangement of possibilities, might sit closer to the base of reality than distance or duration. This is not because information sounds poetic, but because black holes, entropy, and quantum theory all keep pointing toward it. When matter falls into a black hole, its detailed structure seems lost from view, yet the entropy of the black hole increases in precise proportion to the area of its boundary. That proportionality suggests that the fundamental bookkeeping of the universe may be surface-like, encoded in ways that do not care about volume in the ordinary sense. If the deepest accounting is two-dimensional while our experience is three-dimensional, then geometry may be a kind of translation layer, a way that information organizes itself so that large-scale observers perceive depth and distance. In such a picture, space-time is not discarded. It becomes an effective description like pressure in a gas. Pressure is real and measurable, but it is not fundamental. It arises from microscopic collisions. Likewise, curvature would arise from microscopic informational relationships. Entanglement becomes especially important here. When two quantum systems are entangled, their combined description cannot be split cleanly into separate parts. The state of one is woven into the state of the other. Some mathematical results suggest that the amount of entanglement between regions correlates with the geometry that connects them. Strong entanglement corresponds to shorter effective distances. Weak entanglement corresponds to larger separations. If you imagine an immense network of quantum bits, each entangled in intricate ways with others, then geometry might be nothing more than a map of those entanglement strengths. Space would not be an empty container in which entanglement happens. Space would be the pattern formed by entanglement itself. Time, in turn, might correspond to changes in that pattern, the steady updating of relationships as quantum states evolve. In this view, the familiar smoothness of spacetime would emerge only when the network becomes large and highly connected, the way a woven fabric appears smooth only when seen from a distance. Other approaches explore discreteness more directly. Instead of beginning with continuous curves, they propose that area and volume come in tiny indivisible units. These units are unimaginably small, far beyond current experimental reach, but they impose natural limits. If there is a smallest possible chunk of area, then curvature cannot grow without bound. Singularities, which appear in classical relativity as infinite density and infinite curvature, would be replaced by extremely dense but finite configurations. The infinities would signal not physical impossibility but the breakdown of a smooth approximation. Just as water appears continuous until you zoom down to molecules, spacetime may appear continuous until you reach a scale where the granularity matters. At that point, the equations of relativity would give way to more fundamental rules describing how discrete elements connect and rearrange. This shift in thinking also reshapes how we consider the accelerating expansion of the universe. Dark energy is often described as a mysterious component that fills space uniformly, pushing galaxies apart. But if space-time is emergent, dark energy might not be a separate substance at all. It could reflect properties of the underlying informational network. Perhaps as the network evolves, its large-scale geometry naturally stretches. Perhaps the tendency toward expansion is encoded in the microscopic rules that govern how connections rearrange. The fact that dark energy appears uniform across space suggests it is tied not to particular objects but to the structure of spacetime itself. If spacetime is a large-scale effect, then dark energy might be a large-scale signature of deeper dynamics rather than an independent ingredient. Cosmic horizons deepen this perspective. Because the universe expands and light has finite speed, there are limits to what we can observe. Regions beyond a certain distance are forever causally disconnected from us. In a purely geometric picture, this is a consequence of stretching space. In an informational picture, it may represent a boundary in correlation. Beyond the horizon, states are no longer entangled with ours in ways that allow signals to reach us. The horizon becomes not just a geometric sphere but a limit to shared information. This reframing does not change the observable facts. It changes the language in which we interpret them. Instead of saying space expands and carries galaxies apart, we might say correlations thin out as the underlying network evolves, and geometry responds accordingly. Inflation, the rapid early expansion, also fits naturally into an emergent framework. Tiny quantum fluctuations, normally confined to microscopic scales, were stretched to cosmic proportions. These fluctuations became the seeds of galaxies and clusters. That process hints that the boundary between quantum and cosmic is not absolute. Microscopic uncertainty can imprint itself onto the largest structures in existence. If spacetime emerges from quantum relations, inflation may have been a moment when those relations reorganized dramatically, smoothing and stretching the emergent geometry in a way that left visible traces billions of years later. All of these possibilities remain incomplete. They are sketches rather than finished portraits. Yet they share a common quiet theme, that the fabric metaphor may be too literal. Spacetime might not be threads woven in a background void. It might be the macroscopic appearance of countless microscopic connections. The smooth curves guiding planets and bending light could be the average behavior of a deeper system humming beneath perception. If so, the next steps in physics will not simply refine equations of curvature. They will seek the patterns from which curvature arises, patterns subtle enough to hide behind the steady ticking of clocks and the gentle drift of galaxies, waiting to be recognized as the deeper rhythm from which space and time themselves unfold. As these ideas unfold, the sharpness of geometry begins to soften into something more relational. Instead of imagining spacetime as a grand arena stretching endlessly in all directions, we begin to imagine a web. Not a web floating in space, but a web whose connections define what space even means. In such a picture, there is no empty container waiting to be filled. There are only relationships, and from the density and structure of those relationships, extension appears. This is a profound shift. It means that emptiness is not a void but a region of minimal correlation. It means that distance is not measured by rulers laid across a pre-existing grid, but by how tightly or loosely pieces of the universe are intertwined. If that sounds abstract, consider again the analogy of temperature. When countless molecules move chaotically, their average kinetic energy becomes what we call heat. No individual molecule contains heat in isolation. Heat is collective. In the same way, spacetime curvature might be collective. No single microscopic element would possess curvature. But when enormous numbers of underlying degrees of freedom interact, their combined behavior could resemble curved geometry. The bending of light near a star would then be the large-scale response of this collective system, not the deformation of a literal sheet. Gravity would not be a force and not even purely geometry in the classical sense. It would be the thermodynamic tendency of an underlying network to arrange itself in ways that, when averaged, produce the equations of relativity. Some researchers have explored precisely this possibility, deriving gravitational-like equations from statistical principles. In those derivations, the smooth laws of general relativity arise naturally from assumptions about entropy and information flow. The equations do not need to be imposed. They appear as conditions of equilibrium, as though spacetime geometry were the state toward which a deeper informational system relaxes. That perspective reframes Einstein's equations not as fundamental laws, but as effective equations, similar to how the laws of fluid dynamics describe water without referencing individual molecules. They are accurate and powerful, yet they belong to a higher level of description. If geometry is emergent, then time may be as well. Time, in relativity, stretches and contracts depending on motion and gravity. But in quantum theory, time often appears as a fixed background parameter. This mismatch has long troubled physicists. An emergent perspective offers a gentle resolution. Perhaps time is not fundamental in either theory. Perhaps what we call time is the measure of change in correlations within the deeper network. As entanglement patterns evolve, the sense of before and after emerges. The arrow of time, the reason we remember the past but not the future, could arise from the growth of entanglement and entropy. Instead of time flowing like a river, it might be that correlations reorganize, and our consciousness rides that reorganization, interpreting it as flow. The accelerating expansion of the universe also takes on a subtler tone in this framework. Dark energy becomes less a mysterious fluid and more a sign that the underlying network favors configurations corresponding to increasing large-scale separation. If the microscopic rules permit or encourage expansion, then geometry will reflect that tendency. The fact that dark energy appears constant across space suggests that it is woven into the large-scale structure itself. It may not cluster like matter because it does not arise from localized particles. It may be a property of the network's ground state, the baseline configuration toward which it naturally evolves. Cosmic horizons remind us that there are limits to shared information. Beyond a certain distance, regions of the universe can no longer influence one another. In a relational view, this means their entanglement with us has effectively diminished to zero. The horizon is not merely a geometric boundary but an informational one. It marks the limit of correlation, the edge of mutual influence. Over immense spans of time, as expansion continues, more regions will slip beyond this boundary. The observable universe will shrink in informational terms, even if it grows geometrically. Future observers may see a darker sky not because galaxies vanish, but because correlations fade beyond reach. Even black holes, once symbols of absolute mystery, begin to fit into this gentler narrative. If their entropy scales with surface area, perhaps they are not devouring information but redistributing it along boundaries in ways that preserve the deeper accounting. The event horizon could act as a kind of informational membrane, encoding interior details in subtle correlations. When black holes merge and emit gravitational waves, those waves may carry imprints of the underlying network adjusting to a new configuration. The ringing geometry would be the audible echo of deeper rearrangements. None of these ideas claim finality. They remain exploratory, mathematical, incomplete, yet they converge toward a single quiet suggestion: that reality might be less about things and more about relationships, less about positions in space and more about patterns of connection. If that is true, then our experience of living in spacetime is like standing on the surface of an ocean without seeing the currents beneath. The surface is real. The waves are measurable. But the deeper motions give rise to everything we observe. As the conceptual edges soften, the urgency to pin down exact mechanisms gives way to a slower wonder. The universe does not feel diminished by the possibility that spacetime is emergent. It feels layered. The stars continue their silent motion. Galaxies drift apart. Clocks tick and light bends. Yet beneath these steady rhythms may lie a subtler dance of correlations and information, a quiet architecture from which space and time crystallize. And if the next chapter of physics succeeds in revealing even a glimpse of that deeper layer, it may not replace spacetime. It may simply show us that what we thought was the foundation is, in fact, a beautifully woven surface resting on patterns far more delicate and far more profound. As we let these ideas settle, something interesting happens to the feeling of solidity we normally attach to the universe. The ground beneath you does not become less firm. The stars do not flicker out. But the sense of what is fundamental begins to loosen. Instead of imagining reality as built from tiny bricks arranged in a vast container called space, we begin to imagine it as built from interactions, subtle, constant exchanges that collectively give rise to the appearance of space and the flow of time. In this quieter view, existence is less like architecture and more like music. Notes do not sit inside a container. They arise from relations between frequencies. The melody is not stored in a box. It emerges from structured vibration. If spacetime is emergent, then what we call a location may be nothing more than a stable pattern within a larger informational process. When you point to a star and say it is over there, the there might be shorthand for a set of relationships linking that star to you through light, gravity, and quantum fields. Distance becomes a summary of interaction strength. Duration becomes a summary of change. The geometry that feels so continuous may be the long wavelength behavior of something far more discrete and restless beneath. This possibility reshapes how we think about the limits of knowledge. If spacetime itself dissolves at extremely small scales, then asking what lies beneath it may require abandoning spatial language altogether. We are accustomed to asking what something is made of, as though there must be smaller pieces stacked below. But if space emerges from a network of relations, then the question where loses meaning at the deepest level. There is no below in the spatial sense. There is only a deeper layer of description. That shift is subtle but profound. It suggests that the ultimate explanation may not resemble particles moving in space at all. It may resemble mathematics describing patterns that only later become geometry. The early universe hints at this layered nature. During inflation, spacetime expanded so rapidly that quantum fluctuations were stretched across cosmic scales. Tiny ripples became the seeds of galaxies. The microscopic imprinted itself on the macroscopic. If geometry is emergent, then inflation might represent a dramatic reconfiguration of the underlying network, a phase transition in which correlations reorganized and expanded, freezing quantum variations into the structure we observe billions of years later. The uniformity of the cosmic microwave background, with its faint temperature variations, becomes a fossil record of that transformation. The sky itself becomes a map of ancient informational rearrangements. The accelerating expansion driven by dark energy adds another gentle mystery. As galaxies drift farther apart, more of the universe slips beyond causal contact. Over immense timescales, observers in distant futures may see only their local galaxy, surrounded by darkness. The cosmic web will thin beyond visibility. In a relational picture, this means correlations fade. The network stretches until once connected regions become effectively isolated. Geometry follows that thinning. The observable universe becomes smaller not because space shrinks, but because shared information recedes. There is a quiet humility in recognizing these limits. We cannot see beyond the cosmic horizon. We cannot probe below the smallest meaningful scale without distorting what we attempt to observe. Quantum uncertainty and gravitational curvature combine to shield the deepest layer from direct inspection. Yet this shielding may not be a barrier but a clue. It suggests that the universe has built-in thresholds, scales at which certain concepts simply stop applying. Smoothness stops, position stops, even time, perhaps, stops being a fundamental parameter and becomes a measure of change within a system too subtle to visualize. Future physics may move gently toward this relational language. Instead of asking how objects move through spacetime, we may ask how correlations evolve. Instead of describing forces acting across distances, we may describe changes in connectivity. The familiar equations of relativity and quantum mechanics would remain, but understood as effective summaries of deeper rules. Just as thermodynamics remains valid even though molecules underlie it, spacetime would remain valid even if it is not fundamental. The bending of light, the ticking of clocks at different rates, the orbits of planets, all would continue exactly as measured. But their explanation would shift from geometric fabric to emergent order. This shift does not make reality less concrete. It makes it more intricate. The solidity of experience becomes the large-scale coherence of countless hidden interactions. The smooth passage of seconds becomes the steady updating of relations in a vast informational tapestry. The curvature around a star becomes the macroscopic expression of microscopic structure. What once seemed like a simple stage reveals itself as a layered performance. And perhaps the most striking part is this: we live inside this mystery constantly. Every breath you take occurs within spacetime, whether spacetime is fundamental or emergent. Every heartbeat marks a rhythm shaped by geometry. The expansion of the universe proceeds whether or not we understand its cause. The cosmic horizon limits our view whether or not we interpret it in geometric or informational terms. Understanding deepens appreciation, but existence does not wait for explanation. As the tone softens further, the need for definitive answers fades. The universe has already shown that it does not conform neatly to intuition. Space bends, time slows, quantum states blur and entangle. Black holes encode information on their surfaces. Expansion accelerates. Each discovery loosens certainty but expanded wonder. If spacetime turns out to be emergent, it will not erase these discoveries. It will gather them into a deeper pattern, revealing that what we thought was the fabric is itself woven from threads we are only beginning to imagine. So the future may not deliver a final equation that closes the book. It may instead offer a new language, one in which space and time are chapters rather than the cover. A language in which reality is described not as a stage filled with objects, but as a dynamic web of relationships giving rise to the illusion of stage and object alike. And as we drift closer to that possibility, the sharp lines between geometry and information, between matter and connection, begin to blur into a quieter and more spacious sense of what it means to exist within a universe still unfolding its own explanation. As we reach the quiet edge of this exploration, the need to resolve everything gently dissolves. Theories may continue to evolve, equations may sharpen or soften, new particles may be discovered or entire frameworks replaced, but the deeper realization remains steady. We are suspended inside something astonishingly subtle. Whether spacetime is fundamental or emergent, whether geometry arises from entanglement or from loops or from structures not yet imagined, the lived experience is the same. We wake, we move, we measure, we breathe, all within a structure that bends, stretches, and carries every event forward. If spacetime is like temperature, then what we feel as distance and duration may be large-scale expressions of a deeper microscopic dance. That does not make distance unreal. It makes it relational. It makes it contextual. When galaxies separate as the universe expands, the increase in distance may reflect the quiet reconfiguration of an underlying network. When clocks tick at different rates in different gravitational fields, the variation may reflect how deeply each clock is embedded in the geometry that has emerged from countless hidden connections. Even the arrow of time, the reason we remember yesterday but not tomorrow, might be tied to the growth of complexity, the steady increase of entanglement across the cosmic web. There is something calming about this layered view. It removes the pressure to imagine a final solid foundation, a single indivisible block from which everything else is carved. Instead, reality may be more like a sequence of emergent levels, each arising from the one beneath it. Quantum fields may emerge from symmetries. Spacetime may emerge from quantum correlations. Thermodynamic behavior may emerge from spacetime geometry. Conscious experience may emerge from thermodynamic processes. Each layer real, each layer effective, none necessarily the absolute bottom. Cosmic horizons remind us that our access is limited. There are regions of the universe we will never see. There may be epochs of time we can only infer. If dark energy continues to accelerate expansion, distant galaxies will fade from view entirely. Future civilizations may look out into a darker sky, unaware of the vast structure once visible. Yet even that fading would be part of the same evolving geometry. The horizon is not a wall. It is a limit imposed by the interplay of expansion and the speed of light. It is a reminder that knowledge itself is bounded by spacetime's behavior. And perhaps that is the most grounding thought of all. We do not stand outside the universe analyzing it from a detached vantage point. We are patterns within it, shaped by the same geometry we attempt to understand. Our brains, our instruments, our equations are all embedded in spacetime. If spacetime emerges from deeper informational rules, then our very capacity to ask questions arises from that same foundation. We are not separate observers examining a distant stage. We are localized processes inside the unfolding structure. The future of physics may indeed revolve around information, around the idea that what truly exists are relationships, probabilities, and correlations. Geometry may turn out to be the large-scale bookkeeping of those relationships. Gravity may be the natural tendency of information to organize itself in certain ways. Expansion may be the slow relaxation of a primordial configuration. Inflation may have been a phase change in the deepest network. Black holes may encode more than they conceal. But even if all of these possibilities shift again, the deeper wonder remains intact. For more than a century, relativity has described spacetime as flexible geometry. Quantum mechanics has described reality as probabilistic and entangled. The tension between them has not broken the universe. It has only revealed that our descriptions are incomplete. The mismatch is not a flaw in nature. It is a sign that our perspective is partial. The cosmos itself continues without contradiction. Planets orbit, light travels, galaxies form. Time passes, or at least appears to pass, with dependable regularity. As we let the tone soften completely, we can allow the sharp boundaries of theory to blur into something more contemplative. We may never fully understand spacetime in its deepest form. We may discover that beneath geometry lies information, and beneath information lies structure still unnamed. Or we may find that geometry is fundamental after all, but richer than we imagined. Either way, the mystery does not threaten us. It surrounds us gently, holding every moment of our lives within its vast, dynamic embrace. If you're still drifting with me at the edge of understanding, type 3 in the comments. And now, as the thoughts slow and the questions loosen their grip, let yourself rest inside that quiet realization. You do not need to solve spacetime to live within it. You already do. Every second, whether spacetime is a fabric, a network, a projection, or something entirely beyond our language, it carries you without effort. It curves softly beneath your feet, stretches silently between distant galaxies, and shapes the rhythm of your own heartbeat. We may not understand it fully, but we live inside its mystery every single moment. Let that be enough as you drift gently toward sleep.